With this video, I'd like to introduce you to what an engineer is and to what engineers do. And I couldn't do better to start with by introducing you to Isambard Kingdom Brunel. He lived from 1806 to 1859, and in that short lifespan, he did more to revolutionize virtually every aspect of England than practically anyone in the world. Here he's shown in a very famous image with the launching chains of the ship, the Great Eastern. And this has become an iconic photo as far as engineers go. Look at this cocky guy standing there. He believes he can do anything. And you know, he almost could. Take a look at this. They had no railway back in the mid-1800s between, well, London and almost anywhere. They really, really needed a connection between London and Bristol, and thus was the Great Western Railway born. It was Isambard Kingdom Brunel who built that railway. He was the one responsible for it. Can you imagine? I mean, you really need someone with that kind of cocky sense of, yes, I can do anything, to build something of that magnitude. You can look at a picture of Paddington Station today. Actually is still a mainline station. That was the London terminus of the Great Western Railway. So that was something originally envisioned by Brunel. In fact, there's a Brunel University in England. To get a sense of what things must have looked like when Brunel was alive and designing that railroad, let's take a look at this opening clip from The Great Train Robbery, starring Sean Connery. And you thought engineering was boring. I want to give you a picture of some of the excitement that's behind the scenes. This is right by the building of the Leviathan. That was the Great Eastern, was often known as the Leviathan, one of the very first of the steam-powered ships. Look at the size of the chains. Yes, those are the chains he was photographed by. And here's another picture of him. He's the one here on the right. Look at how cocky again, how he's standing. He would be a movie star if he had been born today. And look at some of the other things he was responsible for building. Here's the suspension bridge spanning the Avon Gorge. Look at the beauty of that. And look here. Here's the Maidenhead Railway Bridge. At that time, it was the largest span for a brick arch bridge ever. Here's another. Look at the beautiful beauty of that bridge. This is the Royal Albert Bridge spanning the River Tamar at Saltash. Again, that was one of Brunel's masterpieces. And here's a picture of Brunel again. Doesn't quite look as flamboyant. I don't think the painter did as good a job. But what I want you to really see is right down here. This is the old-fashioned version of the paperclip that was in use during the time that Brunel was doing his work. Big, wooden, clumsy. Well, there's a lesson in there for us. Every big engineering problem, like building a bridge, a tunnel, a ship, a train, a building, is in reality the putting together of the solution to thousands of smaller problems. Let's take a look at the paperclip. It seems like one of the simplest of objects, but sometimes the simplest of things can hold as much mystery and provide as many lessons about engineering as the most complex. As Henry Petrosky, an engineer himself, points out in The Evolution of Useful Things, the paperclip works because its loops can be spread apart just enough to get it around some papers, and then, when released, it can spring back and grab the papers and hold them. You can see over here what happens to a paperclip that gets bent too much. It just won't spring back into shape. That's because it's reached its elastic limit. The idea that materials have an elastic limit was first explored by Robert Hooke in the 1600s. Yes, that's the same Robert Hooke of Hooke's Law. Now, you might think that making a paperclip is obvious, but it really isn't obvious that one should take a piece of wire and bend it in a certain shape to be able to clip pieces of paper together. Look at the difference between these two paper clips. This is your standard gem-type paper clip. This one, as you can see, look, it's a little bit narrower in this region right here, right? It's not quite as wide. What does that mean? We have to use a wee bit more wire in order to create this paper clip. Also, look, I'll switch this to red. Look at the difference here. See, yeah, this doesn't quite come down as far. Again, that saves the use of wire. But what does that all mean? It means this paper clip may not work quite as well as this paper clip in clipping papers together. Yet this right-hand paper clip will be easier and less expensive to manufacture. These are the kinds of trade-offs that engineers have to deal with in virtually everything they create. Now, before the idea of the paperclip had even occurred to anyone, people used pins, straight pins, to poke a hole in a sheet of paper and clip papers together. Even making a simple pin was very labor-intensive. This illustration gives an idea of how many different people had to be involved in the different aspects of pin making in order to put together the simple straight pin. The famous 18th century Scottish economist Adam Smith estimated that if an individual uninitiated in all the techniques did all the steps on a single pin to create that pin, the output might not even approach 20 pins a day. Yet, if individuals perform separate aspects of that labor, they can together make something like 4,800 pins per day. So separation of labor had its advantages, but that also had its disadvantage. Just think of the intensity and the boredom in putting together something of this nature. Day after day, week after week, year after year, the exact same set of motions. In the 1830s, the American inventor John Howe succeeded in developing an effective pin-making machine. Here's a picture of it from a copy that's on display at the National Museum of American History at the Smithsonian Institution. Now let's go back for a minute. If pins could be made by hand, couldn't paper clips also be made by hand? To make a paper clip by hand, you'd probably have to start much as they used to do with pins. You'd have to take a piece of wire off a spool and straighten it to about 4 inches and then bend it appropriately. Something like this would be incredibly labor-intensive. In 1899, William Middlebrook patented a device to help make the typical gem paperclip, the one we're familiar with today. Look down here at the bottom. This is the key aspect of the device. There were pegs around which the paperclip was wrapped, and that's how the paperclip could be more easily made. Clever and not necessarily intuitively obvious. But this 1899 patent shows us something else interesting. Take a look at this. This is the patent from Johann Weyler he was a Norwegian, he in 1901 filed a patent for something that looks suspiciously similar to the gem paperclip that we're very familiar with today. What this shows is that Weyler's patent was actually filed after a machine was developed to make these types of devices. So clearly Weyler's patent shows that Weyler was not the first to be messing around in this area. In fact, there are hundreds and hundreds of patents showing all sorts of different ways of making a paperclip, each developed in order to try to solve some type of perceived problem with the previous paperclip. If you take a look at, for example, what this paperclip is meant to do is to try and make it so that the clips wouldn't catch on one another quite so easily when they're in the box, so when you pull them out that they stick together. That's what these are an attempt to obviate. Look at also this little lip that's curved up in this particular type of paperclip. That's to allow it to more easily slip onto pieces of paper. So what engineers were trying to do is look at a device, understand what its limitations are, and then try to develop something that surpasses these types of limitations, that finds a way to get around them. So what is the first and perhaps most fundamental role of an engineer? It is to serve as a critic, a creative critic who can both point out what is wrong with a current device and develop a mechanism to make that device better. So engineers are very creative, very perceptive, and they look at things in a new way. Here's yet another analysis, another look at the paperclip. This one's called the Gothic paperclip. Again, it was designed to fill certain needs even as it might create yet other problems. Here's a paperclip that's intended to solve the problem of larger groups of papers. And this paperclip, I rather like this. It's the endless filament paperclip. What this does is you can actually use it to clip papers together, and you don't have to worry about in the normal conventional paperclip. You can have that portion right here of the paperclip can tear and gouge your paper. This is a paperclip that is meant to obviate that sort of thing. Here's another paperclip. This one was filed by Susie Chung Herzl in 1991. What she did was she found that plastic paperclips often broke off if they had to bind a thick bunch of papers. So she made this little part right here that allowed the clip to fasten more easily onto many pieces of paper at once without breaking off. So again, what do engineers do? They serve, number one, as critics. And number two, they serve as creators. People who devise new ways of doing things with hundreds and even thousands and even hundreds of thousands of creative engineering types looking at problems of interest to all areas of society. We're able to gradually make things better for everyone. But how is this possible? Why do engineers do this kind of thing? Is there something different about their brain? Let's take a quick look at how the brain develops and then see if we can better understand how engineers do what they do.
This animation shows brain development from conception through birth. In the first 4 weeks after conception, neural tissue known as the neural plate forms in the outermost layer of embryonic cells. The neural plate folds to form the neural groove, then curls to form the neural tube. This tube differentiates into the forebrain, the midbrain, the hindbrain, and the spinal cord. The forebrain will develop into the cerebral cortex, which translates sensory stimulation. It also controls complex behaviors, thoughts, memories, and problem solving. The midbrain will develop into a neural relay station for sending information from the body to various sites in the brain. The hindbrain will control the most basic physiological processes, such as breathing and heart rate. The spinal cord is the pathway for conveying information between the brain and the rest of the body. Between weeks 4 and 8, the embryo grows rapidly and the face becomes recognizably human. The eyes on the side of the head begin to migrate forward and two distinct hemispheres of the cerebral cortex emerge. Between weeks 8 and 26 of the fetal stage, the cerebral cortex grows to cover the midbrain. By week 28, a major structural change begins. The cortex expands greatly in surface area and becomes wrinkled and folded inside of the skull. Beginning at week 28 and continuing through week 40, the brain surface fills with hills and valleys, called gyri and sulci. These cerebral folds and wrinkles help to create a vast neural network, which allows the brain to become a highly flexible yet precise control center and processor of information.
Now you may wonder, how would the development of the brain have anything to do with how engineers think? Well, it turns out it could have a lot to do with how engineers think. One preeminent psychologist, Simon Baron-Cohen, and yes, he is the cousin of Sacha Baron Cohen, if you'll remember, from Borat fame. But at any rate, Simon has posited that people generally perceive the world in two different ways. One is by empathizing, putting oneself in the shoes of another person, feeling the emotions. The other approach is through systemizing, that is thinking rationally and logically about issues. Two very different ways of looking at the world. Baron-Cohen posits that as those two hemispheres of the brain are developing, one preferentially receives influence, so it develops a little faster than the other side. All of this is very little understood, but it does seem to relate to how we do perceive the world. There does seem to be neural differences in how engineers, mathematicians, mechanics, and so forth perceive the world and how their brain interacts with the world, as opposed to those who are empathizers, such as nurses, kindergarten teachers, and therapists. Nothing's wrong with either approach, unless, of course, you try to use one approach when the other one is a little better. Baron-Cohen's approach be related to those of Daniel Kahneman, the Nobel Prize winner in economics. He wrote this wonderful book, Thinking Fast and Slow. Kahneman posits that we have two deep-rooted neural approaches to looking at things. One is, of course, the fast, and the second is the slow way of thinking. Fast would be something like, what's 2 plus 2? Oh, you immediately know what the answer is. You feel it intuitively. It's 4. You've had it drilled into you. Slow system would be something like, what's 248 times 962? Well, that would take a lot of slow thinking to figure it out. You can figure out, but it's not natural and it doesn't come easily. And that was actually part of his Nobel Prize winning work, was to realize we will often jump to the conclusion that something is correct using our fast system, then build later on it with our slow rational system. But the problem is that often our fast system of intuiting something can be completely incorrect. And our slow system, which builds on that, can then make its decisions based on the wrong input. Why do we do this? It's because thinking slowly, thinking about these kinds of issues that are much more complex, is harder for us to do. Some brains appear to be more practiced. They're able to do it more easily. But it seems not too natural to think in a slow, methodical, rational fashion, and our brains really aren't geared for it much of the time. We're lazy. We would rather do this kind of thinking than this kind of thinking. Engineering training, as it turns out, helps to develop this slow, rational thinking. So even if you don't have it very much to begin with, training your brain in an engineering fashion can help you make better, rational decisions when you need to. So what do I mean when I say that? I mean we can actually change our brain. Even if the brain initially develops with certain propensities, we can, through concentrated attention and focus, change our brain. This is one of my favorite books in that regard. I highly recommend it. I know from myself, I started out, I flunked mathematics in high school. I would have been the perfect, typical person who said, I hate technology, I hate science, I want nothing to do with it, because that's the way I was. But I changed myself through trying to do that, paying attention, focusing, being forgiving with myself, but also gradually teaching myself how to learn the sciences, how to learn mathematics. So what that shows is the brain is capable of marvelous plasticity if you focus your brain. Another very important point to realize along these lines is the idea that you can really change yourself, and the way to do that is through the stories you tell yourself. If I had told myself in high school, I don't have an engineering brain, I can't do that, I would have believed myself and then just ended up not having this wonderful career where I can understand and even help develop some innovative, new, creative approaches to things. So this book here by Timothy Wilson talks about how you can help change your brain by the stories, the simple stories you tell yourself. And every great engineer knows one thing at the deepest level. Their ideas about how they can change the world can actually change the world.